Okay, let's get started. Any questions or comments about the course? Okay, just a quick comment about homework. So, as you know, homework is due today, and I just wanted to give you a little bit of feedback on what format you should put your homework in. And this is not really won't affect your grade, but I think this is just something for you. Most of you are very neat when you do your homework, which is great. And the reason this is a good thing is, believe it or not, you're going to probably come back and look at these homeworks in a couple years, maybe 5 years. You may be doing a design of an amplifier, and you might want to know, well, what was the relationship between swing and noise in a in a loaded stage? And if you just don't remember it, probably should remember it. But if you don't remember it, you're going to look up your homework. Also, when you do your homework, you want to really, in some ways, you should think of it as a note to self. When I look at this in 5 years, am I going to understand my notation? Am I going to understand where I did my simulation? So you might want to put, a little note, simulation files in this subdirectory, right? It's a good thing. Trust me. You'll come back and you'll look at these, and you'll appreciate the fact that you took time to do it right. Okay. All right. So let's get back to where we were last lecture. Last lecture we were in the middle of analyzing the noise of a switch capacitor gain stage, and we handled the noise in phase 1, and we're about to look at the noise in phase 2. And it occurred to me that before we look at that in detail, it's probably a good idea to kind of review what we've learned about noise. And a lot of you have taken 142, and you're coming in with a different perspective on noise, just like I did actually coming into this class. Because for so many years doing RF, and you have a different perspective on noise. Here we care about total integrated output noise, and so the perspective is a little bit different. So let's look at a couple of very simple examples to see where this perspective is coming from. So okay, previously we analyzed a common source amplifier, and now I don't want to redo the analysis in detail. What I'd like to do is just to give you some intuition for where the result comes from. In particular, why is it that we always get something like KT over C? Right? Is it that we're just cooking up examples where the answer comes out to KT over C times something, or is there something more fundamental? Clearly, there's something more fundamental going on. Okay, so very quickly, let's look at a very simple amplifier, common source amplifier, and we want to find the total output noise. Okay, and if we just take this circuit and transform it into a very simple equivalent circuit that we know how to analyze, looks something like this. Now, in these analog circuits, typically we have a large capacitor at the load, CL, which more or less dominates the transfer function. So the bandwidth is determined by CL. That actually simplifies things. That means that, let's call this CL effective, the total capacitance sitting on this node. That means I don't have to worry about the details of the amplifier and all its poles and zeros. I'm going to assume that this amplifier has been properly designed so all its non-dominant poles actually fall high enough so that they don't affect the stability of this amplifier. So really, this is the only capacitor I need to consider. So I'll put that over here, CL effective. Okay, well, what's the resistance looking out from this capacitance? Well, it sees the output resistance of this transistor, and it sees RL. Let's say RL dominates. Okay? And then what's the noise that's actually being integrated on this capacitor? Well, the noise is the noise of this transistor. I drain with variance equal to 4 kT gamma times GM. Okay? Now, what's interesting about this problem, let's also include the noise of this resistor, so 1 over RL. What's interesting about this problem is I can rewrite it in the following form. I could say the noise going onto this capacitor looks like just the noise of this resistor times some factor gamma GM RL. So this is the excess noise that's due to the transistor. Now, if this excess noise term were not here, what would be the total output noise on this transistor? KT over CL, right? So clearly, since this term is constant, it just comes out of the integral. And so the total output noise is KT over CL effective times, and of course this is the voltage gain, 1 plus gamma the voltage gain. Okay. So the point of this example is we didn't have to do any kind of algebra, we didn't have to do any kind of detailed analysis, and we get this really nice result, right? And now if I change this to a cascode, how does the result change? It doesn't change by much. Well, at high frequencies, right, we know the cascade starts contributing. But we've all analyzed that problem. We know that there's basically, if I replace this with a cascode, then there's a little extra factor, let's call that little NF, which accounts for, let's call it NF cascode, which accounts for the extra noise you get from the cascode. But it doesn't fundamentally change the answer, right? That's the important point. Well, what about when we put feedback? So let's do the same problem. This time, I'm going to make my device an OTA, and I'm going to apply feedback. Let's call this CF. Let's call this the parasitic capacitance sitting on this node, and this is the sampling capacitor, and this is the load capacitor. Okay. So anybody want to guess what the answer is going to be? Just intuitively, without doing any algebra. I'll give you a hint. Try to imagine transforming this circuit into an equivalent like this with some total noise, some resistance, let's call that RO, and then some capacitance CL. Okay? So what's the total noise voltage going to be? Well, everybody knows it's going to be KT over CL times something, right? So what's that something? Well, let's take an extreme example, okay? Let's say that this is noiseless, just for simplicity. And let's say your feedback factor in this amplifier were equal to 1. In other words, these are very small capacitors, right? And this is a very large capacitor. So most of the signal just feeds back, and you have a feedback factor of 1. What would that something be in that case? Okay, somebody volunteering? No? Okay, how about Michael?
So I would say that the feedback is then, it's basically diode connected, isn't it? So
Essentially, yeah, that's right.
So we have 1 over GM here, and basically it's the noise of the transistor then. But,
so what's the something factor?
The drain.
The drain?
Current noise of the transistor.
No, because something should just be...
Yeah, the GM cancels out, basically.
Yeah, exactly. So what do you get at the end? 2? Why do you get 2? 1 plus 1. Yeah, I know 1 plus 1 is 2, but... Okay, very good. You actually get 1 plus gamma. And, in fact, if we just do a simple analysis, okay, yeah, it's actually very good. So you get 1 plus gamma. Everybody understand where this result came from? So the way to think about this is that when F goes to 1, RO goes to 1 over GM, right? And this noise current, IO squared, is gamma times GM. So in this case, we have a situation where, again, the noise bandwidth is very much related to the noise, right? This GM cancels out. Where does this extra factor of 1 come from? Well, this noise leaks into the input and makes its way back to the output. But the intuition here is that when F goes to 1, this factor here between 1 and 2, right? Okay, very good. So what about the general case? In the general case, let's say f not equal to 1. What is RO? Come back to the circuit here. If I wiggle this node, how much current flows, right? Well, let's ignore the current that flows in the capacitors. Well, then that current is mainly coming from this transistor. How much current flows in this transistor due to a wiggle here? Well, if I wiggle this node here, the gate wiggles by a factor of f, right? That's the feedback factor. And then the current is GM times larger. So this is let's just draw a simple equivalent circuit. Let's say I have GM Vy. So let's say this is my test source Vx Ix. And I have a feedback circuit, let me call this capital F, that generates Vy. So Ix is approximately equal to GM Vy, which is equal to GM F times Vx. And so Ix over Vx is GMF. And so R out is therefore 1 over GM times F. Okay? So what's F? Let's look at the circuit. F is, if these are fairly large capacitors, right, then F is really just the feedback factor formed by this voltage divider. So the voltage divider, let's see if I can get that in. So the voltage divider, so I will call V gate over V out, is basically this impedance, which is 1 over CS plus CP, divided by 1 over CS plus CP plus 1 over CF. And I can write this as CF over CF plus CS plus CP. Okay? And this is the factor F. Okay? Yes, questions? Debo.
So this looks like just a shunt feedback. So CF. So how is it different? Like even with resistor, I saw in one of the lecture notes. So how do we feedback voltage? Because inherently in a shunt feedback, we are feeding back current. So is it different because of switched capacitor?
Well, what I'm doing here is, so, these categorizations of shunt feedback, series feedback, they're very good, but at the end of the day, I know what I'm interested in is knowing the output impedance of this device, right? And so at this point, all I care about is what's the kind of feedback connected to this node. Because I'm connecting shunt feedback at this point, this will lower the output impedance, right? Okay? So forget what kind of feedback it is, right, at the input. From the output perspective, I know that the impedance is going to be lowered due to this feedback. Okay. Okay, so, all right, so coming back to this equivalent circuit. So we need to now, we can say that this term is 1 over FGM, and this term here is 4KT gamma 1 over GM, and let's forget the extra factor. There is an extra factor in there because there's feedback, but I just want an intuitive result here. And so now you could see that the total output noise should just be different from KT over C by this factor of F and this factor of gamma, right? So in other words, total output noise is KT over CL, and well, let me just let me write it this way. So the noise bandwidth is proportional to 1 over F GM CL. The noise is proportional to basically 1 over GM. Sorry, GM. Okay. And so clearly the GM is going to cancel out, and we're going to just get a result that depends on this factor f. And there's a gamma and a 2 and all that stuff in there. But intuitively, this is the answer. Okay? So again, let me emphasize that I'm just after intuition here. I'm not after a perfect answer. And the reason I'm after intuition is that at the end of the day, when I do a simulation, right, more than likely I'm not going to analyze this by hand if it's a very complicated circuit. But at the end of the day, I want to look at my simulation result and say, does it make sense to me? If I vary f, does the answer change in the right direction? So with that in mind, let's look at this example that we went over very quickly a few lectures back. This was called the so-called big noise example. And now it's a cascode amplifier, right? And in fact, it's the same feedback configuration we just analyzed. And now you recognize this circuit as a basic building block for an OTA, right? Okay, so again, here's all the math. Let's forget about it. Let's just look at the final answer. So here is the total output noise. Total output noise is KT over CL times a gamma over F times an extra factor. And this extra factor we know is due to the cascode transistor. So again, without doing any math, just remembering this one result, we can very quickly verify this result is actually right. Yeah, great, this result makes sense. KT over CL, because the GM cancels out with the noise GM. This extra factor, because we get extra noise from the cascode. And this F is my feedback factor. So here's one important point. This is not the feedback factor for the closed loop amplifier. This is the feedback factor seen by the noise transfer function. Okay, any questions about that? All right, so now let's go back to where we left off. Okay. So this is where we left off. And let me just remind you of what we were looking at when we did this calculation. So what we did is we want to analyze the total output noise of this amplifier, and we split it into two phases. We said in phase 1, here's the circuit. In phase 1, I'm discharging this capacitor, and so I pick up a noise, KT over CF, in doing so. And also in phase 1, I'm sampling the input voltage, and here I pick up a noise, KT over CS. Okay. Now I want to see how these noise terms make their way to the output in phase 2. Oh yeah, and then I also did this calculation slightly more carefully by saying, well, in reality, I'm not charging the sampling capacitor with a voltage source. It's being charged with another amplifier. And amplifiers have noise, and so this is the noise factor of that amplifier. Okay. I should admit to you guys, I'm a little uncomfortable with this noise factor notation because it's confusing with noise figure. And also a noise figure, if you don't take the log, you call it noise factor. So it's not the same thing, but I think you guys are smart enough to know the difference. Okay, so now what happens in phase 2? Well, in phase 2, I'm going to take this noise and just multiply it by the gain of the amplifier, right? Gain squared, because we're talking about noise power. So this is the CS over CF is the closed loop gain of the amplifier, and it makes its way to the output. Also, the noise due to this feedback capacitor, CF, basically just directly adds to the output, right? If we look at the circuit again, you can see in phase 2, the op amp is active. This point is a virtual ground, so any noise on this capacitor directly adds to the output. Okay? So those two terms we discussed last lecture. And then last lecture, this is where we stopped. And this now makes perfect sense to you guys, right? No need to explain it. The actual amplifier now is going to contribute a noise KT over CL. This feedback factor takes into account the difference between the noise of the device and its output impedance, right? Its output impedance has an extra factor of F in it. And then this extra factor is kind of all the dirtiness of the amplifier, right? The amplifier has maybe a cascode in it, maybe it has something weird, maybe it has a PMOS current source, and that's going to add another extra factor of 1 plus V star 1 over V star 2, you know, all that stuff. So that's it. That's the total noise. And we can rewrite it in this fashion. which emphasizes that some of the noise is coming from the OTA and some of the noise is coming from the feedback factor. Okay. Questions? Yes.
So usually you can use switch cap circuits for building filters. How do we take into account the transfer function of the implemented filter for the noise?
Yeah, that's actually a very good question, and we'll probably address that later when we talk about filters, but a lot more in the following course, right? 247. But actually something quite nice happens. If you go back to that noise lecture and look at the table of useful integrals, you can see that for most transfer functions, low pass, even with two poles, right, complex transfer functions, the noise bandwidth always comes out to 1/4 1 over RC. And so at the end of the day, for most cases, the same thing happens. You get KT over C times some factor, and that's because the transfer function of the filter tends to do the same thing. So all you need to do is take into account the relative location of the bandwidth relative to the resistance of the transconductor, right? So if the bandwidth is 10 times smaller than the actual transconductance, let's say resistor, then you get 1/10 the noise. If it's 10 times bigger, you get 10 times the noise, right? Okay. So this intuition is very powerful because it lets you very quickly calculate the noise.
So
Devo.
here also, like it assumes that the bandwidth of the circuit is mainly determined by CL for phase 2.
That's true, right? That's actually a very good approximation. All these amplifiers, we'll see when we design these more and more, that in fact CL is the dominant pole of the circuit. Okay, good, very good question. All right. Okay, so now we're going to talk about more realistic amplifiers. We hardly ever build single-ended amplifiers. We always build differential amplifiers. And in fact, we build fully differential amplifiers. So you guys are very used to having just plain differential amplifiers, right? Where you have two inputs and one output. What we're going to talk about is fully differential amplifiers, where you have basically a differential output in addition to a differential input. So first of all, why would I do this? Why build fully differential circuits? And I guess it's a good place to start is why differential circuits at all? Why is it that, you know, when you take a course like 105, you don't see differential, but then when you take 140, it's all differential amplifiers. Why is it that differential amplifiers play such an important role? Okay. Now this is an easy question. Let's get some people who haven't answered before. Get your 5% participation. I have a good memory, so. Okay. Tim. Mike.
It just resists outside interference.
Very good. So differential circuits reject interference. What kind of interference?
Coupling?
What kind of coupling?
The
Any kind of coupling? Let's say I have an amplifier here, and unfortunately there's a capacitor from this node to the power supply. Let's say my power supply is dirty. Is this amplifier going to reject this? No? Why not? Yeah, it's got to be common mode noise. So it rejects common mode interference. And this is actually, you know, I said what kind of interference, and you said coupling, and then I said what kind? You said capacitive. Well, yeah, dominantly capacitive, but actually any kind of common mode interference is rejected, right? It doesn't have to be capacitive. Another example is package. So let's say I'm building an amplifier and I'm packaging it. And so I have these bonding pads, and then I have these bond wires that go to my package. And let's say on the other side I have a power supply. And let's say there's also some digital circuits. And so because of the switching noise of these digital circuits, right? Digital circuits, especially digital circuits driving output pads, they're just big inverters, right? And what inverters, why is it that inverters generate so much noise on the power supply? Asako, you want to, no? Somebody else? Vincent?
Is it because that it drives a huge current whenever it switches?
Yeah, but why does it drive huge currents?
Because it needs to have huge power to drive the pads.
Okay, but just think of the structure of an inverter. What is it about an inverter that drives lots of
It's
current?
kind of just a switch that it connects to power.
Yeah, but it only switches one side, right? So you pull current from the supply and then you dump it to ground. So what's so bad about that? You're right. That's actually a big part of the current, right? If you're driving the output pads, that's a lot of current to charge up those capacitors, and so you draw a lot of current from supply. But also, what's another bad thing about inverters? Yes. Yeah, exactly. During transitions, inevitably, you get short circuit currents, right? Ideally, these two switches are never on together, but we all know there's a time when they both turn on, and if these are big transistors, they short the supply, and so a huge current flows from VDD to ground. Okay? And so all these currents are being drawn from my power supply. And in order to, so because of the inductance of the power supply, I get LDIDT kind of noise. And it's noise, I call it noise, of course it's not noise, but we call it noise because there's so many inverters here all switching at different times that it's kind of pseudo-random, right? And so it looks like a random perturbation. And so how do I fight this? Well, I put a really big bypass capacitor on chip. But I can only make this big, so big. So at the end of the day, I'm going to have noise on this supply. And because this is a large current, it actually will generate a large magnetic field which will couple through the mutual inductance to the inputs. Now if I had a single-ended input, all of this noise would appear at the input of my amplifier and it would get amplified. Right? That would be terrible. But because this, if I make my arrangement, if my package is symmetric, then for the symmetric component of the input, it gets canceled out as common mode. So it's only the asymmetric part that will generate signal. So when you design your package, you don't do it blindly. You actually look at the most sensitive nodes in the circuit and try to make sure that they have a symmetric relationship with noise sources. Okay? So for instance, if you can't put your supply right here, you might have two supplies, and you might be able to put one here, and hope that they have roughly the same signal, and so you pick up common mode. Okay? Questions or comments? All right, that's fine. That's differential. But why fully differential? Why does the output need to be differential? Anybody? So for instance, if I didn't go fully differential, one argument I could make is that, well, then you're going to pick up noise on the output, right? And then you actually would like to go into another differential amplifier to reject that noise, but somehow I need to generate a differential input. And I can't really use a bail-in, right? Low, RF frequencies, I'd use a little bail-in on chip and generate a differential signal, and then that would again reject the common mode. So it's nice. These differential signals can drive each other. Is there another benefit? Yes. Yeah, swing. So fully differential circuits have twice the voltage swing. So a single-ended circuit, right, could swing all the way up to VDD, right, minus some number of VD sats, and all the way down to VSS. Whereas this circuit can flow effectively, the differential output can go all the way to VDD and all the way to minus VDD, right? And so the swing is actually twice VDD minus some saturation voltage. And that's, of course, very important because the signal-to-noise ratio at the output goes like the voltage squared. So by going differential, we actually get a 4x benefit. Of course, the noise goes up too because we're differential, but hopefully the noises will add uncorrelated, so we end up getting an SNR benefit in going differential. Okay, so nowadays when you build circuits, it's almost obvious to go differential, especially because you're usually integrating your analog circuits with other things, and you want to get as much noise immunity as possible. And without even thinking too hard, if you go differential, you're going to reject a lot of noise. Okay, and so we talked about the noise pickup in the package. I think a few lectures back we talked about the noise pickup in the substrate, right? So just remind you that if this is an analog transistor, it's an analog NMOS, it is actually exposed to the world. It's almost like this NMOS is sitting right next to the freeway, and every truck that passes by makes it shake, right? Because it has these capacitances, and this substrate is like an international freeway shared by everybody. So there's lots of noise currents flowing in here and coupling into our circuits. And the good thing is that if I have two transistors which are close together, then their noise pickup will be roughly the same. And so a differential circuit will reject this. Okay. Obviously, if I had a triple well option, that would help as well to get more isolation. Okay, so back to fully differential circuits. Actually, let's go back to the slide. Okay, so one of the important things about differential circuits is that they respond only to differential inputs, right? Ideally, they completely ignore the common mode signal you give them. And we characterize that by the common mode rejection ratio and how much differential gain we have versus how much common mode gain we have. Okay, and we can actually think of the input signals at each terminal as having a common mode component and a differential input voltage, right? So we like to think of exciting our circuit with these kinds of signals, and likewise on the output there will be a common mode output voltage and a differential mode output voltage. Well, here's a practical issue. How do you actually generate differential signals in SPICE? And there's actually a lot of ways to do it, right? You could use controlled voltage sources. You could take a single-ended signal and then split it into two with a controlled circuit. What's the issue with doing that? Why is that probably not a good idea to do? Let's use controlled sources. So I have V in, let's say some fake resistor, and then this will be plus V in, and this will be divided by 2. This will be minus V in divided by 2. Okay. This is fine. You can do it. But there's actually a better way of doing it, because anybody want to point out a problem with doing something like this? Yes, Christian.
Is it that you haven't set up your common mode?
Yeah, I could do that, right? I could now put a common mode voltage here, right? Well, one of the issues with this circuit is that source impedance now is 0, right? And what I'd really like to do is actually drive my circuit with the right source impedance, right? And likewise, if I put a load on the circuit, I want to make sure that I'm truly loading the circuit. So this is why balins are actually very convenient. So let's switch here. Now I'd never actually use a balun, right? But this is just for SPICE. So in SPICE, it's very convenient to use baluns to generate differential mode signals. So here, this output, so if I come in with two input signals here, this node is only sensitive to the common mode signal. And so if you're familiar with baluns, this is very obvious. If you're not, you might want to take a little bit of time and analyze this circuit. This signal here is, in essence, the difference between these input voltages. So it is the differential input voltage. And I can use it the other way around. I can apply a voltage here, and this will give me a differential signal over here. And if I can apply a common mode signal, and that gets summed onto both of these terminals. So in SPICE, you can use a little building block like this and just put it in your library. And anytime you need to generate differential mode signals, this is a convenient way of doing it. It's a lot less messy than having all these controlled generators in your circuit. Okay, so here's an example of how you would do that. So here is a fully differential amplifier, and this is the balun basically on the input. This is the balun on the output, and you can see here I want to have 0 input common mode, so I just ground this terminal, and then from this terminal I drive it with my input voltage. And here a fully differential signal will develop with a common mode of 0. And then on the output I can measure the common mode signal by just tapping this node and looking at what voltage I see. And I can take a single-ended load now and put it here, and I know that automatically the right differential load will be presented to my amplifier. Okay. Questions about that? Yes?
Can you explain how the coil to present VC and VDC?
Okay. Probably we can talk about this offline, because I don't want, this is just an aid, right? I don't want to make this lecture balun. We could talk 10-15 minutes about this. But come to office hours today, we can talk about it. This is just basically an aid. So when you're running simulations, you have this balun and you can use it. If you don't understand how it works, definitely take the time to understand it. But once you have this, it's a very nice, convenient function.
Yeah, that's for simulation, but what if you want a real chip? You said that for RF you can use, but what if not RF circuit?
Yeah, so if you're using this in a real chip, basically your analog circuits are going to be embedded somehow. Almost everything they do is on chip. They pretty much don't need to interface to the real world. So usually analogs, for instance, the example that I know best is RF. The RF interfaces with the outside world, then creates a digital baseband signal, which is differential. Then you have several differential stages of amplification and filtering, and then you have a basically digitization process. So you never have to worry about this issue if you're designing integrated circuits. Designing circuits that interface with the outside world, then you need some stages that do conversion for you. And what's a simple way of converting a single-ended signal to differential? Right? Diff pair, right? If I ground the input of one diff pair and drive the other, the output's a pretty good differential signal, right? And vice versa, how about if I want to take a differential signal and make it single-ended? Not really, right? You could take the output of one side of a diff pair, right? Or, if you don't want to waste the signal, you'd mirror the signal over from the other side. Okay. So, if you actually had to do this in real life, there's lots of ways of doing it, but here's a very simple way. This is a differential signal, right? Plus, minus. Okay, so let's talk about some figures of merit for fully differential amplifiers, and it's probably hard to see, so let me write these actually a little bit bigger. So what's ADM? ADM is just the differential gain. It's the differential output voltage divided by the differential input voltage. Okay, and for a very good op-amp, right, for a very good OTA, this should approach infinity. Should be very large. Okay. What about the common mode gain? This is the common mode output voltage when you put in a common mode input voltage. Okay? And of course, we'd like to completely reject common mode signals, and so we'd like this to be 0. Okay? Actually, I don't care too much about this. This doesn't really concern me too much because I'm building differential circuits, so I already know my common mode is going to get rejected. What I do care about more is conversion from a common mode signal to a differential signal. This is bad, right? I don't want to have any differential signal at the output when I have input common mode. Okay, this is what I really care about. And of course, I'd like this to be equal to 0. Okay. What else is important in a fully differential amplifier? Any other useful gains? Matthew?
Power supply rejection.
Yeah, very good. So I want the gain from VDD, which is the differential output signal for a small signal excitation on VDD, to be 0, right? And of course, the same with ground. So what am I talking about? Well, I have an amplifier, fully differential, and I put a little small signal on VDD. So this is the noise on VDD. I don't want it to generate a differential signal. If it does, it's a really bad differential circuit. Okay? And a good metric to define for these amplifiers is ratio of desired to undesired. So if the figures of merit are kind of the desired gain over the undesired gain. And we want this to approach infinity, and we want this to approach 0, so we kind of get this double infinity. So this thing should really approach infinity. Okay. So common mode rejection ratio is the differential gain over the common mode to differential gain. And some textbooks will define this as ADM over ACM. Again, I don't really care about ADM over ACM. What I really care about is how much what's really undesirable is for a common mode signal to become a differential signal. Okay? Power supply rejection ratio, very important. PSRR, not PSSR. Again, that's the differential gain divided by the gain from VDD. Again, infinity. And also, so this can be defined for VDD and for VSS. Okay, questions or comments? Okay, so this was the example I showed you guys earlier. And so what we're going to do is compare basically all the figures of merit for this fully differential amplifier and then the single-ended amplifier, right? So this amplifier is an OTA where we just ground one input and drive the other input. And so here's VSS, here's VSS and VDD. Right off the bat, and of course, again, this is an OTA that I'm going to use for a gain stage. And the reason I put these big resistors here is because I don't want to have to mess with switches, right? So you just put big resistors and then the circuit will bias up correctly and work and give you gain even at low frequencies. And then I use these building blocks here to go from a single-ended signal to a fully differential signal. Okay. All right, so these are just simulation results. So first of all, interesting, what's the power supply rejection of the first circuit? So in this first circuit, if I vary the power supply, VDD, I'm seeing a signal at the output. Does that make sense to you guys? What's going on? What's the probable cause of this finite power supply rejection ratio? It's only 40 dB, right? 40 dB is not so much. Well, there's probably some capacitance, right, between VDD and the output. And so you're getting a signal feed through directly to the output. If that were the case, then this would go up with frequency, right? But it's flat with frequency. So what's causing it? Well, it's probably then some cap divider, right? Because cap divider's frequency dependence drops out, and so it's more or less flat once you get up to a high enough frequency. So if you look in here, for instance, there's a cap divider at the input with this capacitor. And so if there's any capacitance from this point to VDD, that's going to generate a signal from supply. On my fully differential circuit, I also have the same problem. I have this parasitic capacitances at the inputs, but what's the power supply rejection ratio is very good. Of course, that's because it's a balanced circuit, so it's rejecting that input. Okay? So this is a good example that shows you a fully differential circuit rejects the power supply, but the simple differential circuit did not. Also, why is just 300 dB? Should it be larger? That's just numerical noise, right? It's finite precision, and so really it should be infinite for a perfectly balanced circuit. Here's also a plot of the gain. So this is it's kind of hard to read, but these are the various gains in the circuit. You can see, for instance, this is again the gain from VDD and VSS to the differential output for the fully differential circuit. And really this, that's captured by this ratio here. Okay? Okay, so this is kind of let me switch. Yeah, let me switch over here. So, okay. So again, continuing on with fully differential circuits, let's just discuss 3 different ways you might build a fully differential circuit. Okay? And this is basically the input. So I could build a fully differential circuit like this. Okay. I could build a fully differential circuit like this. And usually, of course, these will be current mirrors or active loads. And then finally, I can build a fully differential circuit if the process allows me like this. Okay? So clearly, just comparing this case 1 and 2, I prefer case 1 because it has basically less headroom, right? I don't have this extra current source. But almost universally, I'm going to use a current source when I design the circuit. Why is that? So first of all, let me ask you a simpler question. What's the common mode? If I apply a common mode signal to this guy, what differential output mode do I get? Okay, 0, right? Okay. That's pretty good. That has infinite common mode rejection. But why is it that everybody uses this circuit, even though it has basically headroom issues? Okay? You mind using the mic? Otherwise the people on tape won't hear it.
So that current source gives you infinite source resistance for common mode signals, and that degenerates the GM of those transistors, so you don't see any common mode gain coming up.
Yeah, but we just pointed out that if I apply a common mode signal here, I have common mode gain, right? But that's okay, because there's no differential signal.
I mean, your VIC to VOC will be much higher for the first one.
Yeah,
VOC over
but
VIC.
I'm going to drive another differential stage which is going to reject the common mode signal anyway, right? Okay, so You're pointing out the fact that there's common mode gain. So if I ground this node and I apply common mode signal, let's say plus plus, then the common mode output signal minus minus, so the common mode gain, which is the output common mode over the input common mode, is pretty much the GM times the RL, right? But as I said, I don't really care too much about this common mode gain because I'm going to drive another differential stage and I can reject this. Okay. So why is it that I still prefer to put a current source down here? You might even argue that the current source not only does it require headroom, but also is going to burn up, is going to add noise to the circuit, right? So why use that current source?
If common mode gain is higher, then common mode to differential mode gain will be higher too.
Okay, so what I care about is common mode rejection, right? And this circuit has basically, so what this is a differential mode. So this is the output differential mode. What I really care about is differential mode for an input common mode. And in fact, the differential mode here at the output is 0 when I have an input common mode. And so I'm happy, right? This is kind of what I want. Okay, very good. Mismatch, right? So what if you have a mismatch? So let's look at that. Okay, very good. So now, clearly we have a problem. Because if I apply common mode input signal, then the output differential mode is basically delta RL. Let's say I have an RL mismatch times GM V input common mode. Or if I don't have an RL mismatch, I have a delta GM mismatch. Okay? So in this case, the differential mode, so this would divided by the input common mode, we call this ACMDM. And the differential mode gain is just GMRL. So we can write this common mode rejection ratio as ACDM over ADM. And that gives us delta RL over RL plus delta GM over GM. Okay? So now this circuit's common mode rejection ratio is just a function of matching. So if I tell you you get 0.1% matching, what's the common mode rejection ratio? $60 dB, right? Very simple. So for instance, if I have a 1% match, then I would have 40 dB common mode rejection ratio. So that's why I put a current source here, right? So now let's look at what happens when I put a current source. So again, I apply a common mode signal. And I'm interested in the differential output signal. And now even if there's a mismatch, right, what's the common mode gain? How small is it? Well, let's think of the equivalent half circuit, right? Equivalent half circuit, I double this resistor, and this is RL, and the gain, so I call this just the common mode gain, is RL over 2 RSS, right? Approximately. Because if this is large enough, the GM of this transistor doesn't matter. and this is very small, right? So now the common mode output is going to be ACM times the common mode input, which is practically 0, right? And so now I'm taking a very small number. So then again, the same would apply here. So my common mode rejection ratio would be RL over 2 RSS times the same delta RL over RL plus delta GM over GM, right? Because this is the common mode signal that's generated, and that flows into the output and produces a differential output signal. In fact, here the delta GM wouldn't matter because the gain is really determined by RSS. Okay, so now you could see that if RL is, if this is a mega ohms and this is 10 mega ohms, and clearly it's going to add a factor of 20 to 40 dB, right? I can easily muster another 20, 40 dB of improvement here. Now, of course, you might argue that, wait a minute, what if I have an active load, right? In which case, these resistances would be on the same order of magnitude, right? What saves me? So this is actually not the common mode rejection ratio. This is the common mode output. This is the differential mode. For common mode input, this is the differential mode output. So if I look at the common mode rejection ratio, I have to divide this by the differential gain, which is just GMRL, right? And so then you see how I end up getting, so this is 2 RSS. So then this RL cancels out, and you end up getting a factor of 1 over RO, the output impedance again. So you actually get a big improvement. 1 over GMRO kind of improvement. So if you can get a gain of 20, 30, that directly improves your common mode rejection ratio. Okay, that makes sense to everybody? All right, so let's look at, let's keep on this topic a little bit. So what if let's just say I'm now using relatively small RLs, let's say a kilo ohm, and I just really go crazy I say I have lots of headroom, and I really want to improve my common mode rejection ratio, so I'm going to do a triple cascode current source here. Do you think I'm going to see that improvement? In other words, does this reject all the differential mode output signals by just totally, does this completely kill the common mode gain of the signal? What other sources of differential output can we have? Talked about delta GM and delta RL. Yes. VT offset. We can lump that into delta GM, right?
Cascode MOSFET also contribute the noise.
Okay, we're not talking about noise, right? You're right. Sure. Actually, let's come back to this noise topic. I'm glad you brought it up. So, does this current source contribute noise compared to this guy? Should we be worried about the noise of this current source? Okay. Lee, you're shaking your head. Why not?
Because noise is a common mode signal.
Okay, good point. Because the noise actually, if this is a fully balanced circuit, the noise comes here, sees the same impedance going left, going right, and so it goes into the output and it creates a common mode signal. So if we're designing a differential signal, great, I don't have to worry about the noise. Is that always true? Christian?
Well, not if you have mismatches, right?
Okay, but noise is small to begin with, right? So the noise times the mismatch is very small. But yeah, you're right. Let's say the mismatch is 1%, so then you get 1% more noise. Any other situations we should watch out for? Well, actually, most of the time what you say is true. And that's because usually this is going to be in a feedback circuit. And the feedback circuit is going to force the plus and minus terminals to always be roughly at the same potential. And so that means that the impedance here is really equal to the impedance here. But under transient conditions, right, when the feedback hasn't been able to restore the balance, this transistor may be on hard, this one could be off. All the noise could go here and generate differential noise. So actually, under transient conditions, you will get extra noise. So watch out. Okay. So that kind of takes care of the noise. And so your argument was, well, we don't want a triple cascode because we're going to get more noise. Yeah, but again, the noise is not that important. For feedback cases, circuit is balanced, the noise is common mode signal. So I still would like to find out why I should be concerned about this circuit. So if you've never answered a question before, answer this one and you'll get your 5%. Okay, yeah, I see you saying it, but use the mic and say it. Don't be shy.
Body bay.
Yeah, that's right. Body effect. So ultimately, remember, for most NMOSs, the source node, right, is connected here, but the body is grounded, right? And that means that as I vary the source voltage, I'm going to excite a voltage source to body. And if the transistors have a mismatch in their body coefficient, I'm going to get an output differential signal, right? It's that simple. So here, remember the output of a transistor is GM-VGS plus GM-VBS. There's a back gate. It's easy to forget this back gate, but it's always there. And usually it doesn't matter, but here all of a sudden, because the source voltage is getting so large, right? So for a common mode signal, this is just a follower. So whatever voltage I have here, I have here. If I apply a very large common mode signal, it appears at the source, and that will generate two extra current components, right? And if these two current components are mismatched, then you end up getting a differential output signal, even if everything else is matched. Okay? All right, so let's come. Oh, yes, question.
Connect the body to the source.
Okay, why can't we do that? Well, sometimes we can, right? But only in a triple well process, right? Usually the NMOS is actually not, you don't have that option. So you might wonder, why would somebody use a PMOS input stage when, in fact, NMOS transistor is better, right? You see a lot of op-amps with PMOS input stages. And who can give me 3 reasons why I would use a PMOS input stage? One you all should know by now. Okay, one is body effect, right? I can tie the source to the body and I get rid of that body effect. What are 2 other good reasons?
One is flicker noise.
Flicker noise, yeah. We talked about this before. PMOS devices, being subsurface devices, have better flicker noise performance. So we can get better flicker noise performance if the transistor is actually, if the physics of the transistor makes the current flow under the surface. Unfortunately, that's kind of going away in modern technology. You'd still see an advantage though. Okay, what's another reason? This one you probably don't know unless you've taken a course like this. Christian?
I was just going to say that since it's in a well, it picks up less noise from the substrate, but that's probably not what you're looking for.
Okay, well that's a good point. Yeah, that's a valid point. So let's go for 4.
Tunneling.
What's that?
In the PMOS, tunneling
Tunneling.
less likely to happen.
You know the device physicists in the course when they mention things that you wouldn't think of. No, tunneling, okay. Actually, it's a valid point. I mean, if you're designing a deeply scaled OTA and you worry about charge, right? Maybe the PMOS device has better tunneling, and so you get less leakage. Okay, it's an interesting point. 5. All right, so probably most of you haven't studied slew rate before, but slew rate limiting is another issue, and you actually want lower GM if you're worried about slew rate limiting. So that's something we'll come back to later. Okay, let's come back to the slide here. And this is basically 3 SPICE experiments, if you can read it. First one is the grounded source differential pair. This one's a true differential pair with a current source. Sometimes this is called a pseudo-differential pair for the reason that it doesn't have the current source. And then finally, a PMOS differential pair where we're able to tie the body and source together. Okay? And so here's the simulation results. So here's the common mode rejection. This is the common mode rejection. I guess we introduce here an intentional mismatch. So you see the W over L's are not quite equal to each other. You probably can't read that. But this one is 10.05 over 1. This is 9.95 over 1. And same thing for all 3 of them. Okay? So again, you had about a 1% mismatch, and so you got 40 dB right off the bat. Didn't need to do any analysis to see that. Now you add this tail current source, and you get a huge improvement, right? Wow, that's a huge improvement. So you're up to more than 70 dB of common mode rejection. Why is it going away at high frequency? Okay, Dable?
Because the capacitance of the tail current source.
Yeah, exactly. So to get good common mode rejection ratio, you need really high impedance at that source node. And if you've got capacitance sitting there at high frequency, that's going to basically reduce the degeneration. And so the common mode rejection ratio will go away. Fortunately here, if the transistor is not too big, then you actually get it all the way up to maybe even the signal frequencies where you care. Okay? And then finally, this is the PMOS device where we've gotten rid of the body effect, and now we see huge common mode rejection ratio, right? Really, really nice. Why is it that the frequency starts dropping faster for the PMOS devices?
Yeah, I used to thinking that you kind of keep the GM the same, so the PMOS should be large, so the capacitance. But that's only twice. I don't know why it's kind of like more than twice.
Yeah, that's a small factor, and here it's actually a huge factor, right? Yeah. Anybody else want to take a stab at that? Yeah, let's look at the circuit. Effectively, if the common mode rejection ratio is worse, that means there's more capacitance on the source node. So where's that coming from? Okay, Drew? Yeah. Why did I put in an extra capacitor here, right? Am I just evil? This is actually a very good thing to think about. Whenever you put down a PMOS device... Okay, Phil?
There's capacitance between the well and the substrate.
Very good, right? Because now I've tied my source to the body, and I see that full well capacitance. And that could actually be quite large. So that's why, you know, in SPICE, if you don't tell it, SPICE knows nothing about the well. So you have to actually explicitly add a capacitor here to model that well capacitance. Okay, very good. Okay, so these plots now make sense. Let's move forward. And so this is just a summary slide, and again, probably hard for you guys to read, but this is just a summary of kind of the back of the envelope calculations that we did here for differential mode gain, common mode to differential conversion, and then finally common mode rejection ratio. Okay? So you can go through this in detail on your own. And then this is just a summary. So I think we've said most of this, but let's quickly check it. So without a tail current source, yep, we're limited by matching. Oh yeah, it says something I didn't say is another problem with this circuit is that what determines the bias current when we ground the source node, right? Well, the input common mode signal determines the bias current. That's pretty bad, right? You want the bias current to be constant, not a function of the common mode input. So if you have the option of AC coupling, you could say, well, I could hold the common mode constant with a DC biasing circuitry, and then I would AC couple, and so then that would be okay. Well, if you had that privilege, then you wouldn't worry about common mode anyway, right? So if you are worried about common mode, then you have to think about it. So for most situations, this is really impractical. Tail current source, we improve the common mode rejection ratio, and at high frequencies, we're limited by that capacitance there. Tie the well to the source, we get rid of this extra GMB matching constraint. But the well capacitance actually ends up hurting our high frequency performance. Okay. All right. Any questions on this? All right. So we have about 10 minutes, and just wanted to show you some simulation results on a simple common source amplifier. And really, by now, we've talked about this so much that I think everything you see here is going to be pretty obvious. But a couple of things I want to point out. So first of all, this is a common. So you might say, why? We just talked about all these great differential circuits. Why back to the common source? Because this is really the heart of any kind of differential amplifier, right? For differential signals, it's going to be a common source stage or a cascode stage. So really, we can understand the performance of these half-mode circuits and then gain intuition for what happens in a fully differential circuit. Okay. I actually probably just want to point out a couple of things with this. So again, this is very straightforward. I'm using a PMOS load, and in homework you analyze what the effect of the noise is on this PMOS load. We can also verify that. First of all, here's the DC input-output characteristic. So I just sweep the DC input and plot the output, and a digital designer would look at this and say, ah, it's an inverter, right? And the analog designer says, ah, it has lots of gain, right? What's interesting in particular is the gain really goes low when the output signal gets large, right? So for large input voltages, my gain gets very low at these edges, right? Almost zero. And this is actually something important that I want to discuss. So if I go into SPICE and I plot the small signal gain, I get this first curve here. And this curve really is just a derivative of this, which tells me that out here, my gain goes to 0. And this is as a function of the output voltage. So it looks like for high output voltages, the gain is really bad. And likewise for low input voltages. But then I plot the large signal gain, right? The large signal gain is how much the output deviates from its DC point versus how much the input deviates from its DC point, right? And if I plot that, neglect this little point here, I get this red curve, which in fact shows that for large signal conditions, I actually have a wider range where the gain is, let's say, bigger than 20, if that's the spec I'm trying to get. Okay. First of all, which is really important, small signal gain or large signal gain? And two, why is the large signal gain better? Okay, so while you think about that, let me just explain this point here. This point is just the fact that as I cross V out 0 and V in 0, I get 0 over 0, and that should give me a nice finite value, but the numerics here are off. So this is a numerical thing. Really, the curve should be smooth. Gain doesn't drop to 0 here. Okay. But, so coming back, which is more valid, the large signal gain or the small signal gain? Okay, the large one. Why? Well, first of all, notice that Mr. Murphy is absent from this graph, right? Murphy's law always tells us that things are always worse than you think they are, right? And here, all of a sudden, we realize that large signal gain is what we care about, and boy, we get more output range with large signal gain. So that's actually a good thing. One of those times where what you care about actually is better. So why is it I care about the large signal gain? Let me give you a hint. Think about the applications that we're thinking about. We're going to use this as a gain block in some switch capacitor circuits. Well, let's go back to small signal gain. Why? What the hell is small signal gain, right? Small signal gain is the gain you get when you apply an infinitesimally small signal at a given operating point. So if I'm, let's say, at this input operating point and I apply a very, very tiny signal, then the slope I get here is the gain, right? But that's not really right? Because I'm actually going to, in transient conditions, my amplifier is going to see pretty large input signals, right? My diff pair has 0 differential voltage at the input. Boom. Sampling capacitor comes on. I see 500 millivolts, let's say. That's a large signal, right? And so what really matters to me is how much the output responds to that large signal input. So it's really the large signal gain that I care about. And this curve doesn't tell me that much about the large signal gain, right? This curve, for instance, tells me, I think if you look at the extreme case, this curve tells me that my gain looks something like this. In other words, the small signal gain, let's call that G, is 0 out here, right? So this curve is telling me that if my output signal let's plot this as a function of V out. So this is G as a function of V out. So I've inverted the curve, but who cares? It doesn't change the argument. The argument I want to make is that this curve tells me if your V out ever gets to this point, you have no gain. That's not true, right? I still have gain. The reason I still have gain is that if I look at the so the gain, the large signal gain, is delta VO over delta V in. So delta V in is some positive number, right? And delta VO is still, this is delta VO. Actually, sorry, this is delta VO. So I've still got gain, right? So delta VO is not equal to 0. So I still have gain not equal to 0. The difference is that if the amplifier had not saturated, my delta VO would have been that. So I would have had more gain. But it doesn't mean the large signal gain has gone to 0. Okay? And this is actually a very important point, because this large signal gain is what we care about. And so when you run SPICE, don't look at the small signal gain. Look at the large signal gain. It's actually going to give you better results. So if I say, what's the output range over which the gain is bigger than 20, you can see that you actually have substantially better results, especially at the high end here. Okay? All right, frequency response, I think I've pounded this into your head enough. You know that if GMRO is large enough, really CL determines the frequency response. And there's no surprises there. Noise, I also think you pretty much, by doing the homework, you know what's going on here. This is the noise of the NMOS only. This is the noise with the PMOS. And basically, the noise enhancement factor is given by a ratio of the bias voltages, right? The overdrive voltages. So to get low noise, you're going to bias the PMOS transistor with a large overdrive voltage, right? To get good signal-to-noise ratio, though, you have to weigh the fact that signal power goes like the square of V star, right? Whereas noise is just linearly proportional to V star. So clearly there is an optimum point. You don't want to make V star too large, because then your signal is going to suffer. Okay. All right, I'll stop there.